Voltage fault current refers to the maximum possible fault current that can flow through an electrical circuit when a direct short circuit occurs between 2 points with negligible impedance. This condition is often simulated in electrical system analysis by bolting together the 2 points, hence the term bolted fault. Voltage fault current is a critical factor in arc flash calculations because it determines the maximum potential energy that can be released during an electrical fault. According to the NFPA 70 standard, arc flash calculations must consider the incident energy, which is the thermal energy released during an arc flash within a specified distance. The voltage fault current, represented as IF, can be calculated using the formula IF equals volts divided by impedance. In this formula, volts represents the voltage in volts of the circuit, and impedance represents the impedance in ohms of the circuit. Several factors affect voltage fault current. Firstly, voltage level. Secondly, circuit impedance, which includes resistance, inductance, and capacitance. Thirdly, power sources and their impedance. And fourthly, the presence of any fault current limiting devices, such as fuses and circuit breakers. Voltage fault current is a key parameter that helps determine the potential severity of an arc flash. A higher voltage fault current indicates a greater potential for a high-energy arc flash, which requires more stringent safety measures. By understanding the voltage fault current and its impact on arc flash calculations, electrical engineers and safety professionals can accurately assess the arc flash hazard, design and implement proper safety measures to protect personnel and equipment, and comply with electrical safety standards such as NFPA 70. Let's delve deeper into each of these aspects. Consider the voltage level. Higher voltage systems generally have the potential to deliver higher fault currents. For instance, a 480-volt system will typically have a higher voltage fault current than a 208-volt system, assuming all other factors are equal. This is because the same impedance will result in a larger current flow at a higher voltage, according to Ohm's law. Circuit impedance is another significant factor. The impedance of a circuit is the total opposition to current flow, encompassing resistance, inductance, and capacitance. Resistance is the opposition to current flow due to the material's properties, inductance is the opposition to changes in current flow due to magnetic fields, and capacitance is the opposition to changes in voltage due to electric fields. Lower impedance leads to higher fault currents. For example, a short length of heavy gauge wire will have a lower impedance than a long length of thin gauge wire, resulting in a higher voltage fault current if a short circuit occurs. Power sources and their impedance play a crucial role. The strength of the power source, such as a transformer or generator, and its internal impedance directly affect the available fault current. A large transformer with low impedance can deliver a significantly higher fault current than a small transformer with high impedance. The system's design must account for the potential fault current contribution from each power source. Fault current limiting devices are designed to reduce the magnitude of fault currents. Fuses and circuit breakers are common examples. Fuses interrupt the circuit when the current exceeds a certain level, while circuit breakers trip open to break the circuit. These devices help limit the duration and magnitude of the fault current, reducing the incident energy in an arc flash event. Understanding the impact of voltage fault current on arc flash calculations is crucial for electrical safety. Arc flash is a dangerous phenomenon that occurs when an electrical fault creates an arc, releasing intense heat and pressure. The incident energy, measured in calories per square centimeter, is a key parameter in arc flash calculations. It represents the amount of thermal energy a worker could be exposed to during an arc flash event. The higher the voltage fault current, the greater the potential incident energy and the more severe the arc flash hazard. Accurately assessing the arc flash hazard is essential for selecting appropriate personal protective equipment, or PPE. NFPA 70 provides guidance on arc flash hazard assessment and PPE selection. It categorizes arc flash hazards into different levels based on the incident energy. Workers must wear PPE that provides adequate protection for the specific hazard level. This may include flame-resistant clothing, face shields, gloves, and other protective gear. Designing and implementing proper safety measures is critical to protect personnel and equipment. These measures may include engineering controls, such as arc-resistant switchgear and remote racking systems, as well as administrative controls, such as lockout-tagout procedures and arc flash training. Engineering controls aim to reduce the likelihood of an arc flash or to mitigate its effects, while administrative controls focus on safe work practices and procedures. Complying with electrical safety standards such as NFPA 70E is mandatory in many jurisdictions. These standards provide detailed requirements for electrical safety in the workplace. Compliance with these standards helps ensure that electrical systems are designed, installed, and maintained safely, and that workers are adequately protected from electrical hazards. In summary, understanding bolted fault current is essential for arc flash safety. It is a key parameter in arc flash calculations and helps determine the potential severity of an arc flash event. By understanding the factors that affect bolted fault current and its impact on arc flash calculations, electrical engineers and safety professionals can accurately assess the arc flash hazard, design and implement proper safety measures, and comply with electrical safety standards. Let's consider some practical examples to illustrate these concepts. Imagine a scenario in an industrial facility with a 480 volts electrical system. A large transformer with a low impedance supplies power to the system. If a short circuit occurs at a panel board, the bolted fault current could be very high, potentially exceeding tens of thousands of amps. This high fault current would result in a significant arc flash hazard. To mitigate this hazard, the facility would need to implement appropriate safety measures, such as installing arc-resistant switchgear, providing workers with appropriate PPE, and implementing lockout-tagout procedures. Another example could be a commercial building with a 208 volts electrical system. A smaller transformer with a higher impedance supplies power to the system. In this case, the bolted fault current would likely be lower than in the industrial facility example. However, an arc flash hazard would still exist, and appropriate safety measures would still be required. The specific safety measures would depend on the calculated incident energy and the requirements of NFPA 70E. To accurately calculate bolted fault current, electrical engineers often use specialized software tools. These tools can model the electrical system and calculate the fault current at various points in the system. The software takes into account the impedance of all components in the system, including transformers, cables, and protective devices. The results of these calculations are used to determine the appropriate arc flash hazard level and to select the necessary PPE. It's important to note that bolted fault current is a theoretical maximum value. The actual fault current that flows during a short circuit may be lower due to factors such as arc resistance and the response time of protective devices. However, it is essential to use the bolted fault current for arc flash calculations to ensure a conservative and safe assessment of the hazard. Continuous monitoring and periodic review of electrical systems are crucial for maintaining electrical safety. Changes in the system, such as the addition of new equipment or modifications to existing circuits, can affect the bolted fault current and the arc flash hazard. Regular inspections and maintenance can help identify potential problems and ensure that protective devices are functioning properly. Arc flash training is an essential component of any electrical safety program. Workers who may be exposed to electrical hazards must be trained in the hazards of arc flash, the proper use of PPE, and safe work practices. The training should be tailored to the specific tasks that workers perform and the electrical systems they work on. Effective communication is also crucial for electrical safety. Workers must be informed of potential electrical hazards and the safety measures that are in place. Clear and concise labeling of electrical equipment can help workers identify potential hazards and understand the necessary precautions. Regular safety meetings and toolbox talks can provide a forum for discussing electrical safety issues and sharing best practices. Furthermore, the selection of appropriate overcurrent protection devices is paramount in mitigating the risks associated with bolted fault currents. Circuit breakers and fuses must be carefully chosen to interrupt fault currents quickly and effectively, thereby limiting the duration and magnitude of arc flash events. Coordination studies are often performed to ensure that overcurrent protection devices are properly coordinated, so that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. In addition to traditional overcurrent protection devices, current-limiting fuses can be used to significantly reduce the magnitude of fault currents. These fuses are designed to interrupt fault currents very quickly, limiting the let-through energy and reducing the potential for arc flash. They are particularly effective in applications where high fault currents are anticipated. The grounding system also plays a critical role in electrical safety. A properly designed and maintained grounding system provides a low-impedance path for fault currents to flow back to the source, facilitating the operation of overcurrent protection devices. Ground fault protection devices can detect ground faults and quickly interrupt the circuit, reducing the risk of electrical shock and arc flash. Moreover, regular inspections of electrical equipment are essential for identifying potential problems before they lead to failures. Inspections should include checking for loose connections, damaged insulation, and other signs of wear and tear. Infrared thermography can be used to detect hotspots in electrical equipment, which may indicate loose connections or overloaded circuits. These hotspots can be addressed before they cause a fault or fire. Remote racking systems provide a safe way to operate circuit breakers from a distance, reducing the risk of exposure to arc flash. These systems allow workers to remotely open and close circuit breakers, eliminating the need to stand in front of the equipment during operation. Arc-resistant switchgear is designed to contain the energy of an arc flash, preventing it from spreading to other equipment or personnel. This type of switchgear is typically used in high-risk applications where the potential for arc flash is high. Another important consideration is the use of voltage-rated tools and equipment. Workers should always use tools and equipment that are rated for the voltage of the electrical system they are working on. This helps prevent electrical shock and arc flash. Furthermore, the proper use of insulated gloves and other personal protective equipment is essential for protecting workers from electrical hazards. Gloves should be inspected before each use to ensure that they are in good condition and free from defects. The importance of lockout-tagout procedures cannot be overstated. These procedures are designed to ensure that electrical equipment is de-energized before work is performed on it. Lockout-tagout procedures involve isolating the equipment from all sources of energy and placing locks and tags on the disconnecting devices to prevent accidental energization. In addition to the technical aspects of arc flash safety, it is also important to foster a strong safety culture within the organization. This involves promoting a mindset of safety among all employees and encouraging them to report potential hazards. Management support is essential for creating a strong safety culture. Management must demonstrate a commitment to safety by providing the necessary resources and support for safety programs. Employee involvement is also critical. Employees should be encouraged to participate in safety committees and to provide feedback on safety procedures. A well-designed arc flash risk assessment program should include several key steps. Firstly, data collection, including gathering information about the electrical system such as voltage levels, transformer sizes, and overcurrent protection device settings. Secondly, short circuit study to determine the bolted fault current at various points in the electrical system. Thirdly, arc flash hazard analysis by using the results of the short circuit study to calculate the incident energy and arc flash boundaries. Fourthly, selection of PPE based on the calculated incident energy levels and the requirements of NFPA 70E. Fifthly, implementation of control measures including engineering controls, administrative controls, and safe work practices to reduce the risk of arc flash. And lastly, documentation and training of all steps involved, including maintaining detailed records of the arc flash risk assessment and providing training to workers on arc flash hazards and safety procedures. Furthermore, regular reviews and updates of the arc flash risk assessment program are crucial to ensure its effectiveness. Changes in the electrical system, such as the addition of new equipment or modifications to existing circuits, can affect the arc flash hazard and require updates to the assessment. Periodic audits of the program can help identify areas for improvement and ensure that it is being implemented effectively. In conclusion, understanding voltage fault current and its relationship to arc flash calculations is essential for electrical safety. By following the guidelines and best practices outlined in this discussion, electrical engineers and safety professionals can effectively assess and mitigate the risks associated with arc flash, protecting workers and equipment from this potentially deadly hazard. Remember, a proactive approach to electrical safety is always the best approach.